like the, it's finance, I like looking at that, so. I like everything else. Right over the end. But it's all good, so you're having it right for the end.
Oops, sorry.
That's good. I don't know there's an end that goes there.
Well, we got a grand total of 8 people here. It is 1 o'clock, so it's always the trouble with this kind of thing is I like to bark at people for not being here, but you guys are the people who are here, so I can't bark at you guys. I've got to bark at everybody else. Anyway, I really appreciate you guys being here and being on time.
I think we're giving out the answers to the midterm today, so.
I need to start doing that. I need to start right at 1 o'clock. There'll be some hint for the test, every single class. That'll get people here on time. Anyway, I'm glad that you guys are all here. I have a quick, logistics, update for you. I didn't get a chance to grade the homeworks that you turned in on Tuesday yet, but I'll get that done in the next day or two. There is another assignment meanwhile that you guys, I'm sure you're all working on it or thinking about working on it, for Tuesday. That's homework number 9. We are halfway through the semester. I think if I looked in my bank of homeworks, there's gonna be 17 of them by the time we're done. So we're almost right in the middle of our semester and in the middle of our homeworks for this class. So that homework will be due on Tuesday. And of course, I have a ton of office hours between now and Tuesday. I'll have hours on tonight, I'll have hours tomorrow night, and also on Monday, and then again on Tuesday. So lots of chances to ask me questions if you have any. I also wanted to mention that we are going to have a quiz next week on Thursday. That is because 2 weeks from today is our second midterm. So I always like to give a quiz a little bit before the midterm so that people can get a little bit of a idea how they're doing and also just to get you to study a little bit. So for next week on Thursday at the start of class. So I will be starting right on time and hopefully you guys will all be here on time. The quiz is gonna cover all of that stuff from chapter 3 since the first exam, as well as section 4.3, which by the way, we're already done with all of that material. The only thing you need to do is kind of get the homework done for Tuesday, because that homework does have some problems from section 4.3 on it. But anyway, so we'll have a quiz on Thursday. Remember, quizzes just count the same as a homework, and we have lots of homeworks, so your quizzes will be diluted significantly by the homework scores. Whoops, oh, that door got, can you unlock that, hit that switch for me on that door? Get that, there we go. Thank you. Yeah, so we're gonna have the quiz on Thursday, and it'll count, just like a homework assignment. I'll give you 20 minutes, something like that, to do the quiz. Make sure you know your definitions, make sure you know your theorem statements. On a quiz where I don't have as much time to ask you questions, I'm more likely to ask you for those quicker answers. What's the definition of an accumulation point? What's the definition for the limit of f of x equals L? Stuff like that. So make sure you know your definitions, make sure you know your theorems. The Bolzano-Weierstrass theorem, there were 2 versions of that. Monotone convergence theorem, monotone subsequence theorem, and on and on and on. Also, you might notice section 3.7 is here. That is a section about limits at infinity. I've decided to not cover that in class. I am gonna make a video, probably tonight, and ask you to watch it. It'll be a required video that I'll have you watch over the weekend, and maybe I'll even make an assignment for it and give you some extra credit for the midterm, something like that, just to watch it and take notes on it, something like that. So anyway, so be looking for that. I'll send an email out once I've got that ready for you. You can see that the midterm is just gonna cover the same stuff that the quiz covers, except 2 extra sections, which we're gonna be covering today. Actually, we should be able to finish everything for the midterm by today. This is very unusual. A lot of semesters, I'm like still teaching the material, like the class right before the exam, and I don't like doing that because it's not enough time for people to learn it. Here we are 2 weeks before the midterm and I'm almost done with all of this material. So that's great. It means we'll have time to really focus in on getting ready for that exam. Just if you want to kind of get your calendar planned out a little bit, I am going to do review sessions again for the midterm, not for the quiz, but for the midterm, I will do review sessions. Seemed like those times worked pretty well last time around, so I decided to go with this again. First of all, on Monday, the 24th, from 7 to 9, I'll do a review. And then again on Wednesday from 4 to 6. Now, as usual, I will be recording the review session, and if you can't make it or don't want to come down at those times, it's okay. I can send out a link with an email to you guys with the video of that. Or you can just come in Zoom and just watch it from home live. That's also fine. Or you can come in person. These will be in the room right outside my office, just like I did for the first exam. So I'm gonna kind of just do that the same way. I'll bring practice problems. We'll just kind of take our time and go through some examples and try to see how people feel about stuff. Okay, and I'll also be adding some extra office hours around this time. I have to be a little careful. The 25th is actually my birthday. I might be gone. Well, I have to teach that day, but probably that night I might be taking the night off. Who knows? But other than that, I'll be around. Also, I did publish a resources folder for you guys. So there is a sample exam in there. There's also a review packet that sort of has all those buzzwords, all the theorems, the definitions, kind of a list of things to be able to do. What are the theorems you should know how to prove, all those kinds of things, as well as some extra practice problems in there as well. So between the sample test, the problems that are in the review packet, and then the problems I'm going to do at the review session, you'll have quite a bit to look at that if you want to. It's all optional, of course, but as much time as you think you need to put into it, there should be stuff there to fill up your time. Does anybody have any questions about any of that? Okay, so anyway, so that's all the important stuff coming up for the next 2 weeks, and that'll take us to spring break, actually. I think the week after the exam is our week off, so we'll be ready for it by then. So that should be good. Okay, so again, I will have a required video that I'll send you an email about over the weekend to just talk about limits at infinity. It's not very difficult. It's just a kind of a standard thing, but I'm going to skip over that and just try to finish up the first 3 sections of chapter 4 right now. Okay, so let me just remind you here of some things on the board. In the box, of course, once again, for like the 3rd day in a row, I've put down the definition of limit of f of x as x approaches c equals L. So the definition of it is very technical. It has epsilons and deltas in it, right? For all epsilon greater than 0, there exists a delta greater than 0, such that if the distance from x to c is greater than 0 but less than delta, then the distance between f of x and L is less than epsilon, right? And we drew the picture with the blue strip going this way and the red strip going this way. I won't redraw that picture today, but this is basically the bare bones definition. On Tuesday, we proved some limit theorems that can be applied using this definition, and those can now be used. So you don't always have to go back to the definition every time you want to prove that the limit of f of x equals L. You can take advantage of these theorems that we've been proving along the way, such as the limit theorems. Limits respect addition, subtraction, multiplication, and division, right? That was kind of the essence of that. And then we also have this result, which I did want to write down here again for you, that we did at the end of class last time, proposition 4.6. This is a theorem, and we did prove it, which basically tells us, well, when will the limit of f of x as x approaches c equals L? Well, one way to look at it is for all sequences that converge to c in the domain. Okay, so the points xn need to be a sequence that are not equal to c. So none of the values can equal c, but we have to have terms that are converging to c. For all sequences that converge to c, if I hit them with F. If I take F of all of those points, the results need to be converging to L. Okay, so that's really it. Of course, it's impossible to consider every sequence that converges to C. So you would never really use the theorem in the backwards direction. You would not typically do that because, I mean, if you were trying to prove that the limit of f of x equals L, I would prefer to take my chances with the epsilon delta definition rather than be forced to consider every possible sequence that converges to C, which is some unfathomable number of sequences, right? So there's just, this is not a very practical proposition in the backwards direction. Rather, the way that the reason that this proposition is important and the reason I bring it up and it's in the book and so on is because it's very useful sort of in the forwards direction to make a contradiction. To say, okay, let's try to prove that this limit does not exist by assuming it does. Assume that this limit does equal L, well then that would imply forward direction, that would imply that for every sequence converging to C in the domain, the image of that sequence would be converging to L. And we did 2 or 3 examples on Tuesday where, oh, well, we created sequences that converged to C, but the f of xn did not converge to a single number L. Either you could make the f of xn sequence diverge. I think there were a couple examples where the sequence was just unbounded. F of xn was just unbounded, and if that was the case, of course, it's not converging to L if it's unbounded. Or another option is, you know, if you had 2 different sequences converging to, whose images were converging to 2 different output values, like an L1 and an L2 that were not the same, that would also be a contradiction to this limit existing. Because if this limit of f of x is equal to L, then there's only one number L that limit can equal, right? Remember, limits are unique. I think that was another one of our theorems, right? So you can't have 2 different limits for the same function as x approaches C. So that's really the way this proposition is used, is to disprove the existence of limits by doing a contradiction or contrapositive of the forward direction. Okay, and so like I said, we did about 3 of those in class last time. I hope that most of that made reasonable sense. Does anybody have any questions so far? It's just kind of summarizing where we left off on Tuesday. So far, so good. Okay, in a little while, we're going to do some group work today. We'll practice some of the stuff that's up here on this first board. But I think I kind of like to break up the class a little bit better. I'm going to start by giving you guys a little bit of a further information here. So we've talked about limits of functions. Everything on this board is limits of functions, and everything on this board you don't even have to have f of c being defined. There doesn't even, C is an accumulation point of the domain of the function. Doesn't even have to be in the domain. It just has to be an accumulation point of the domain. Now I want to start talking about, well, what is actually happening at f of c itself as compared to values of f of x that are close to f of c. So this is the idea of continuity. Okay, so we are now going to go backwards in the book to section 4.1 and start talking about continuity, which is really the main focus of this chapter, okay? So again, I'm kind of going a little bit, in a sense, out of order with this, because the book obviously covers this first, but you're going to notice today how easy these results are going to be, because we've done the hard work over here. We've already proved the limit theorems. We've hopefully got a good understanding of how this definition of the limit of f of x works. It's going to make this real easy, okay? At least pretty easy. I need to be careful. Not super easy, but pretty easy. So I'm going to start right away with the definition of a continuous function. And let's look at the differences of what I'm assuming here as compared to like what I've assumed up here. Okay, so check this out. I'm going to let D be a subset of the real numbers. Okay, so that's just my domain. And f is a function from D to R. Okay, so that's just like before. But here is the first thing that is kind of a difference in this section. notice that C is not just an accumulation point of D, but C is actually in D. It is in the domain of this function, okay? So then here's my definition. We are going to say that F is continuous at C. F is continuous at C if and only if, and I'm gonna give you the sort of wordy neighborhood expression of it first, and then we'll rewrite it using epsilons and deltas again. Okay, so just like we did for limits, let's do that here too. So for every neighborhood, so I'm gonna start by writing it out in words. For every neighborhood V of, now in the limit definition that we were doing on Tuesday, we would have said every neighborhood of L. But in this definition, there is no L. What we have instead, guys, is the role of L being played by F of C itself. So for every neighborhood V of F of C, there exists a neighborhood, which I'm going to call U of C. So that should look very familiar. So far, all of these words are exactly like they were for limits, except that we had an L here, which was not F of anything, it was just some value. So here we have almost the same definition. There exists a neighborhood U of F of C such that if X is an element of U and D, so intersect with D. Okay, now in the definition that we had over there, when we did it in words, we also had to say something about how X had to be in, X had to be not equal to C. There was some condition, because remember the limit as X approaches C doesn't allow X to equal C. Here we're not gonna add that. Here we're not gonna add that. So C is obviously a point, you can tell already, C is in the domain and C is in U, because this is a neighborhood of C. So if X is in that intersection, that includes C itself, then F of X is an element of V. So that part should look pretty familiar. So that is the words way of stating the definition, but I'm going to rephrase this definition right away into the more mathematically technical notation, the way that we really want to be writing it down. So here it is in rephrased form, guys. This is what you will mainly be using. F is continuous at C if and only if. Okay, so guys, every neighborhood of F of C is going to be indexed by some epsilon. So for all epsilon greater than 0, then there has to exist another neighborhood. That one's going to be indexed by delta. So there exists a delta greater than 0, right? Such that if the absolute value of X minus C is less than delta. Now, one thing I want you to notice before I go any further, in the definition of a limit, you noticed I had to say that X minus C was strictly greater than 0. That was because we did not want X to be equal to C. That was not allowed in the limit definition. Over here, we absolutely don't need to rule out X being equal to C. So letting X equal C is perfectly legitimate. We don't have to rule that out. But then the conclusion would just be, as you would probably expect, the absolute value of F of X minus, instead of L, which is what we had over there, now that L is just played by F of C. The role of L is played by F of C, and that should be less than epsilon. In case anybody's nervous that, oh gee, now we have to worry about letting X possibly be equal to C, whereas we didn't before, that shouldn't get anybody too nervous, because if X is equal to C, of course this will be true. Because if X is equal to C, you have F of C minus F of C, which is trivially less than epsilon. So the fact that we are allowing XC equals C here does not make this a difficult definition to satisfy, okay? So this is really the way that we're going to be thinking about it, and I just wanted to mention the subtle differences between this box and that box, right? Okay, one of which is that over here, f of C doesn't even have to be defined, right? C isn't even required to be in the domain, it just has to be an accumulation point of the domain. Obviously here, so if we're gonna talk about f of C, then C had better be actually in the domain this time, okay? That's certainly gonna be required, so that's one difference. And then we're allowing X to be C, as I've already kind of talked about. Just as a sort of a follow-up definition, and this one is just a natural thing to add. If F, so here I'm talking about F being continuous at C. So what if F is continuous, if F is continuous at every C in the domain, so I'll underline the word every. If C is continuous at every element of the domain, then we just simply say F is continuous. So no more of this at C business, we just say F is continuous. If it's continuous at every single point of the domain, then it's just plain old continuous. We don't have to say anything else besides that. Okay, so is everybody with me so far? Okay. Right, okay, well, I am going to try to connect this even more directly to what we did over here. I don't want to have to now reprove everything that we did for limits of functions for continuous functions. So for example, you're probably already aware that if you take two continuous functions and you add them, subtract them, multiply them, or divide them, you'll still have a continuous function. We could prove all of that from the definition, or we could link it back to this theory over here, where we already proved that limits of functions respect addition, subtraction, multiplication, and division. What is the big link between them? Interestingly, it's not a result in the book that's very easy to find. So I have chosen to call this is a remark, but it is a huge remark. So I'm going to refer to it as a huge remark, and if you talk about the huge remark in your homework or your exam or anything, I'll know what you're talking about. And by the way, I also wanted to mention, if I ask you to give me the definition, what does it mean for F to be continuous at C? You can give me either one of these. So this is the wordsy way of saying it, but then this is sort of the math techie way of saying it. And they're both totally equivalent, so take your pick. Generally, this is the one that you're going to be using when you're doing proofs, and I imagine most people generally use this as their definition. I don't tend to see students favoring the one with all the words in it. So anyway, but I just wanted to mention that. So here is the remark I want to make. If C is in the domain, okay, and it is also an accumulation point of the domain. Now, okay, so I better pause for just a minute. You can be in a set without being an accumulation point of that set. Because remember, there's an opposite concept, which is isolated point. Okay, so you might be stumbling over that for a minute. I wonder what happens if C is an isolated point of the domain. So I'll come back to that in a moment. Let's assume for the purposes of this, that my C is actually not only in the domain, it's even an accumulation point of the domain. Again, just a reminder, what does that mean? That just means not only is C in this set D, but any neighborhood around C contains what? Infinitely many points of D, right? You can think of it in those terms. So it's an accumulation point of the domain, and it's in D. So then, if this is the case, then F is continuous at C if and only if, you guys are going to love this. This is the connection that we've been looking for which now we're gonna connect it back to limits of functions. F is continuous at C if and only if the limit of f of x as x approaches C is equal to f of C. So the L value of this limit should just be f of C in this case, right? So this is really easy to remember, I think, at least compared to like something like this, all the words here. This is relatively easy to remember. It's just saying that if a function is continuous at C, then when you plug C into in for x, so if you just plug C in for x, it should agree with what the limit was as x approaches C. So that should make total sense. So in my mind, what I think of is an example like this. You have C, you have your beautiful function coming along here, but if there's a hole there, if there's a hole in the graph, now your L value and your f of C value, they don't agree. And if they don't agree, then this is not continuous. Not continuous, because in this picture, I mean, you guys all know the loose way of talking about continuity, right? That you can explain to a 10-year-old. A function is continuous if you can draw the picture from left to right without picking up your pencil. So that should mean that there's no holes, there's no gaps, there's no asymptotes, right? Nothing like that. It has to just be completely sketchable without picking up your pencil. Well, so here's at least if you use that 10-year-old definition, this picture is not continuous. You have to pick up your pencil to plot f of C up here and then come back. So it's not continuous, and that's confirmed by the fact that f of C is not the same as the limit of f of x in this picture. So it's just a nice way to kind of think about it. Okay, and if we've characterized continuity of a function at a point in terms of what its limit is, then all that stuff we did about limits in the last couple of classes is going to now suddenly be relevant for us here as well. You're going to see this in a few minutes as I start stating the theorems about continuous functions. It's really very nice. Now I should prove this. This is you may think, oh yeah, I know that. That's probably the way you thought about it even in lower division math calculus. But technically we should prove it. In other words, we should connect this definition with the definition over there, right? So it's very easy actually. If you look at this box and you look at that box, they're not very different. And because they're so close, it makes this proof so easy. Let's do it. Let's write it down. I'm so excited. I love this stuff. Let's do the proof. Okay, so let's go forward. Both of these are pretty short. Okay, so let's assume, for the forward direction, let's assume f is continuous at C. And here is what I want to prove. Okay, I would like to prove that this limit of f of x as x approaches C is equal to f of C. How am I going to prove this? I'm going to use the box definition over here to do it. So I'm going to start off with an epsilon and I'm going to go looking for a delta. Okay, so let's just get that set up. Let's let epsilon greater than 0 be given. So to prove that the limit of f of x is equal to f of C, I have to prove this definition. I have to find a delta now, given the epsilon. But since f is continuous at C, I already have a delta from this assumption, right? So I'm assuming this box is true already. So I can already grab my delta from there. So from the definition of continuity, basically the rephrased definition, there already exists a delta greater than 0 such that, I'm just going to copy these words down basically. If absolute x minus c is less than delta, then absolute f of x minus f of c is less than, turns out epsilon is what we want to put there. We could actually put anything here that we wanted, but I'm going to put epsilon. We don't need to tweak the epsilon at all on this proof. We can just Go with it the way it is. Okay, guys, so I have found a delta. Now the question is, does the delta do what we need it to do? Well, here's what we're trying to prove, that we can find a delta such that if this is true, then this is true, but remember that the L value is f of c. Isn't it automatically already done? Right? So let's just check if this is true. So assuming that 0 is less than absolute x minus c is less than delta, if that's true, guys, then of course this is true, right? So if we're assuming that, then we already know absolute f of x minus f of c is already less than epsilon. And so with the L value of f of c, we're already done. It's almost too easy, to be honest with you. It's like I get myself tripped up. What exactly is that saying? It's because the two definitions are almost the same. The only real difference is this little bit right here. Okay, so that makes it super easy. Let me get this proposition out of the way, because I'm going to prove the backwards direction, which is just as easy. And if you're still not sure, let me know. Because sometimes when things are sort of almost a tautology, as we like to call it, it can sometimes bother us. It's like, wait a minute, this is too easy. It really is supposed to just be that easy, though. Let's do the reverse direction, guys. I'm going to put that over here. I'll have a little more room. Make sure I have enough room. Let's go backwards. Let's assume for the backwards direction, yeah, I'm just trying to, you know what, maybe I should add one more thing over here. I'm sorry. All I need to do is just say, so limit as x approaches c of f of x equals f of c. I should at least make it look like I finished that proof. Okay, so just add that one last little line there, which is really just stating the conclusion. Okay, just for your notes, so that when you try to read it again in another few days, it'll hopefully still make sense. Okay, let's assume now that the limit of f of x as x approaches c is equal to f of c. Let's start with that. I would like to prove that f is continuous at c. What's the definition? For all epsilon greater than 0, we have to find a delta. So just like before, we're going to let epsilon greater than 0 be given. And our job is to find a delta. But, sorry? We already have a delta, right? See, the limit of f of x as x approaches c, it exists and it equals f of c. So from this definition, for all epsilon, there already exists a delta. So from definition, there already exists a delta greater than 0, such that I am literally just copying this, such that if 0 is less than absolute x minus c is less than delta, then absolute f of x minus f of c is less than epsilon. So there is no L here. The role of L has been replaced with f of c. Other than that, I'm literally just copying that box. And now what I'm hoping to do is make sure that the delta that we just found satisfies this box, because this is the definition of continuous, which is what I'm trying to prove right now, right? I'm trying to prove the backwards direction. So I want to prove that f is continuous at c. So that means for all epsilons, I've got to find a delta. I've got a delta. Now we just need to make sure it works. Does the delta that we found over there in our proof have this property? That if absolute x minus c is less than delta, let's assume that. Assume absolute x minus c is less than delta. And what I'm hoping is that absolute f of x minus f of c is less than epsilon. Well, not quite. This one we have to take a little hiccup to get past. Because what we know over here is that if 0 is less than x, absolute x minus c is less than delta, then we get the conclusion that we want. But right now, I'm not assuming that 0 is less than absolute x minus c. So absolute x minus c could be 0. Well, that would just mean that x equals c. Right? That just means that x would just be equal to c. So I'm just gonna say, and if x is equal to c, guys, this is definitely true. Okay, so when x equals c, it is clear, can I use that word? I'm always nervous about it. It is clear that absolute f of x minus f of c is less than epsilon. So in that particular value of x, my conclusion is already good to go. So we can ignore that now. We can now say, all right, so assume x does not equal c. So if x equals c, then it's kind of clear, because this just becomes f of c minus f of c, which is 0, right? So it's clear when x equals c that this inequality is good to go. Well, what if x does not equal c? Well, if x does not equal c, then together with this assumption, we would then know, let's just say so that, we would then know that x minus c is strictly greater than 0, but still less than delta. And if that's the case, if 0 is less than absolute x minus c is less than delta, then we already know. Also, we already know, so here we also conclude, again, it's almost too easy because it's already written down. It's already written down, guys, that if 0 is less than absolute x minus c is less than delta, that f of x minus f of c is less than epsilon. We also conclude that absolute f of x minus f of c is less than epsilon. So for all x's that satisfy this, whether they're equal to c or not, the same conclusion follows. And so in all cases, you can almost think of this as a proof by cases. One case is when x equals c, one case is when x doesn't equal c. In the case when x equals c, it's just clear that you just get f of c minus f of c here, which is of course less than epsilon. And when x does not equal c, then we're going to get the proof to follow from the assumption of this limit definition, right? So either way, we get the conclusion that we need, and so thus f is continuous at c. And that's the end of the proof. Yeah, that's the end of the proof.
Proving the huge remark.
The huge remark. This is a big deal. It's, I don't know, the book, as I said, the book is doing things in a little bit of a different order. When they talk about continuity, they don't have this definition yet. So I like to do the limits of functions first and then kind of go back and tie it in with continuity as such. You do have to ask the question here, you know, what if C is in the domain, but is not an accumulation point of the domain? So the huge remark does assume that your value of C is an accumulation point of the domain. So you might be wondering, well, what would we do if C was not an accumulation point of the domain? Well, in this case, C is an isolated point of D. C is the opposite of being an accumulation point. If you remember from the when I talked about accumulation points, if you have a point that is not an accumulation point of a set, then it's by definition an isolated point of a set. And what does that really mean? What that really means, just to kind of have a visual of it, here's C. If I am an isolated point, it means I can make an entire neighborhood around C that has no points of D in it, other than C itself. So C is, of course, in the domain, but there's no other points of the domain there, right? Everybody following what I'm saying here? So if C was an isolated point, then you would have an entire buffer around C that had no points of D in it. Right? And you know what that actually means? That actually means if you make this buffer neighborhood into your U, right here, I'm gonna go back to the word Z definition for a minute, right? I claim that F will always be continuous at any isolated point. No strings attached, no questions asked. Anytime you look at an isolated point of a domain of a function, F will always be continuous there. Why is that? Well, let's check this definition. Would it be true that for every neighborhood of F of C, that we could find a neighborhood U of C such that, well, by the way, I already have found a neighborhood of C here. An isolated point always has this neighborhood. And then what does the such that say? The such that says if X is in U and in the domain. But wait a minute, if I'm inside of U and I'm in the domain of the function, I'm equal to C. Right, because again, this is a buffer, right? This whole neighborhood is a whole bunch of points, none of which are in D. None of them are in the domain, you see. So here you go. This is, so what this says then is, in this case, thus, there exists a neighborhood. So let me put some words to go with my little picture here. There exists a neighborhood U of C such that U intersect D contains, let's just say it this way, I'm sorry, not U intersect D. Let's just say such that U contains no points of D other than C. So we always have to exclude the point itself. So other than C itself, which is assumed to be in the domain from the very beginning here, other than that, no other points in this interval have output values. No other points are in the domain of the function. So you have this isolated point. It's an isolated point of the domain. This entire neighborhood is basically undefined for the function, other than C itself. So you know that exists, and so now I don't even care what your V is, right? For every neighborhood V, I don't care what it is, I'm just gonna keep picking this neighborhood U that I've already been assured of having. I'm assured of having this neighborhood, right? Because it's an isolated point. C, I'm assuming now that C is an isolated point of the domain. Isolated means very lonely point. There's no other points of D anywhere nearby. I'm just trying to make sure everybody's with me. I see people staring deeply into this. Are we following me okay? If I am an isolated point, that means I can make a neighborhood around myself, right, that has no other points of the set in it. So there is no f of x value for anything in this neighborhood of me other than right at my C value, right? So in this case, given the neighborhood V of f of C, we can use U to show that f is continuous at C. And it's really since U intersect D, you take the neighborhood and you intersect it with D, it is literally just C itself. The intersection of U with D is just C, and of course, f of C is in V. So you only have, In other words, what I'm saying is if you're trying to check if your neighborhood works, if this neighborhood U is going to meet this definition, you have to check for every X that's in U intersect D, f of X is in V. Well, the issue is there's only one X that's in the intersection. It's just C itself. And of course, f of C is in V because V was chosen as a neighborhood of f of C. Yeah. So the upshot of this, just as a quick, let me actually state this as a remark. Again, it's not really a result in the book per se, but the remark here is just if F goes from D to R and C is an isolated point of D, then F is continuous at C. You know what, we should call this the tiny remark. Right next to the huge remark. Like, what's the difference? The huge remark tells us when a function is continuous at an accumulation point of the domain, and the tiny remark tells us when a function will be continuous at an isolated point of the domain. And the answer there is very simple. It'll always be continuous at an isolated point. So
is that a true statement still?
which one? This thing?
Yeah.
This example, my domain is this whole entire real number line.
Mm-hmm.
So I don't have any isolated points here in this picture.
Okay, so.
This would be considered maybe an isolated point of the range of the function. Okay, but that's looking now at the outputs. That's looking at the outputs. When we're talking about D, and when we're talking about accumulation points of D or isolated points of D, remember D is actually on the x-axis. It's part of the inputs of the function rather than the outputs. But that's a good point. If I look at the range of this function, this f of C value looks like it would potentially be isolated, which is true, but that doesn't really have any bearing on the definitions that we're making here.
So what would
Okay.
an example of this tiny remark look like?
One second. What was there?
So if it is an isolated point, you can also mean that the limit to x to c is the same as that one.
So if we have an isolated point,
It is satisfied the definition.
we were assuming here, of course, that we have an accumulation point, so we wouldn't even really be speaking about the limit of f of x as x approaches c. If c was an isolated point, that's a really good comment. So when you write down this notation here, you're pretty much assuming that your x is approaching something that is an accumulation point. Yeah. Now, the reason I like to think of this as the tiny remark is that we're not really going to use it very often because there aren't very many examples where we're going to have isolated points of a domain. I mean, if you're doing isolated points of your domain, you're not really doing real analysis, right? If your domain was Z, okay, so your only inputs were the whole number integers, then I could see it, and it's okay, yeah, I guess every single integer is isolated from each other. But when you're doing functions from Z to R, you're not really doing calculus. You're not doing real analysis at that point. So usually the domains that we look at are going to be intervals or the whole real number line or some array. It's going to be some part of the real number axis that's not a discrete set. Like totally the opposite of like discrete math, combinatorics. It's totally the opposite of that. Now we're talking not about points that are isolated so much, but entire intervals of points. So the tiny remark is really tiny in two ways. One is because it's actually pretty trivial. It's an easy thing, just, oh, f is continuous always at any isolated point. But the second way in which it's tiny is that we're not going to see it very much because for the most part, we don't have a lot of isolated points that we're very interested in. Let's do a few examples. These are great questions though, guys. I really appreciate the comments and the questions. You guys are paying attention. let's do some examples. I promised, didn't I promise that this section would be so much easier because we're connecting continuity back to limits of functions? That huge remark is what does it for us. And because of that, now we can do examples really easily. So let me show you what I mean. Because we've already got a good grip over limits of functions. We spent the last couple of classes on that. But let me get some examples up here so we can kind of try to appreciate this a little bit better. Let me come over here. So number one, let's just take f of x equals x squared. Pretty nice function. I claim that this is continuous. Let me just say on R. It's continuous everywhere. Let's write down the proof. Now, do you think I'm going to want to use this definition? Heck no, we don't have to use that definition. We have a better way of checking if a function is continuous, which is to just look at its limit as x approaches any c. So let's just say given a fixed real number c, right? What we know from the limit theorems, and just for your reference, I'm talking about proposition 4.7, which we had done on Tuesday. From those limit theorems, the limit as x approaches c of x squared, as we know, limits, one of the limit theorems says that limits respect multiplication. So I can write it as the limit of x as x approaches c, quantity squared. And what is the limit of x as x approaches c? Just c, right? We actually did that as an example. So this just becomes c squared, which is just f of c. So the limit of f of x as x approaches c is equal to f of c, right? Every c is, so in this case, my domain is the whole real numbers. So my accumulation points of the real numbers is the whole real numbers. So this applies to every c. So f is continuous at c by this huge remark. That's example number one. Do you think there's anything special about x squared here? Or could I do x cubed? Could I do x to the fourth? Could I do x to the fifth? Could I start adding powers of x, subtracting? Well, I could do all of that stuff. So what's that going to give me? All polynomials, right? Ax squared plus bx plus c, they'll all be continuous because it's just adding continuous functions together. And limits respect addition, subtraction, scalars. So all polynomials are continuous. Easy peasy, right? That's just a kind of generalizing what we just did. Maybe I will write down a little bit of a proof here, just so you have a little idea. But again, given a fixed c in the real numbers, we can use the fact that the limit as x approaches c of x is equal to c, sorry, equal to c, and proposition 3.7 to prove that the limit as x approaches c of p of x, I'll call my polynomial p of x, is just the same thing as p of c. So for any polynomial, I'm sorry, that's proposition 4.7. 4.7. Oh, typo. There we go. Yeah. So all polynomials are continuous, guys. You can use that. And what's that mean? That means if I ever ask you about the limit of a polynomial as x approaches a particular number, You can just plug in the number. Okay, just make it that easy. And you probably did that even in your lower division calculus classes. When functions are continuous, you can evaluate limits by just plugging in numbers. That's kind of the idea, right? Now we can go even a step further. Polynomials don't involve division. They just involve addition and subtraction and multiplication. If we allow ourselves to divide by polynomial expressions as well, we get rational functions. And they are also going to be continuous because the limit theorems in proposition 4.7, there was one statement, I realized it didn't prove the one about division, but that is also preserved. Limits also respect division. So a rational function, number 3 here, a rational function, which would be, f of x equals a polynomial p of x divided by a polynomial q of x, is continuous. Now here again, because we have a denominator, I do have to put a little asterisk on this statement. It's not going to be continuous on the entire domain of real numbers, but it will be continuous at all real numbers C such that, what would be my restriction here? Q of C should not equal 0. Exactly. We don't want to have a 0 on the denominator, but as long as we avoid that, we should be just fine. Okay, let's do one more example. Let's define f of x to be equal to, and I'm going to do a piecewise example here. These are kind of nice to work with, I think, for some of these things. And I'm going to make this thing equal to x squared minus 3x minus 18 all over x plus 3 if x does not equal negative 3. So as long as the denominator is not 0, we'll just make it equal to that. But then I'm going to do a weird thing, and when x is equal to negative 3, we're just going to make this function equal to 8. Okay, and what I'm going to try to convince you here is that this function is continuous at every c value except for negative 3. So let's try that. So my claim is going to be that f is continuous at all c in the real numbers except c equals negative 3. There's just one bad point. Let's first prove that it's not continuous at negative 3, and then we'll look at all of the other values. So let's start with c equal to negative 3. Let's take that value first. And again, I'm going to avoid the epsilon delta definition. I'm going to try to use my huge remark, right? And my huge remark just says, oh, let's figure out the limit of f of x as x approaches negative 3 and compare it with what f of negative 3 is. We already know what f of negative 3 is. It's equal to 8. The question is, how does that compare with the limit? Well, let's look at the limit. Let's look at the limit as x approaches negative 3 of f of x. Now, since we are only approaching negative 3, the x value will never be equal to negative 3. So essentially, we can use the top formula as our f of x in that case. So this is just the limit as x approaches negative 3 of the rational function x squared minus 3x minus 18 over x plus 3. So we can just replace that in there because that is the correct formula for f of x as long as x does not equal negative 3, which it doesn't. Right? Remember, x is approaching negative 3, but it's not going to be equal to negative 3. Anybody have any suggestions how to evaluate this limit? I cannot just plug in negative 3 here. You can see immediately the denominator would be 0.
Factor it up, and x is 6.
Okay, this factor is on top, right? So that's the key step. If we factor it in the numerator, it factors as x plus 3, the quantity x plus 3 times the quantity x minus 6. So you might have noticed that already. And what would you suggest I do next? Can I cancel the x plus 3? Remember, x does not equal -3. So if x was some number other than -3, let me ask you again, this is not a trick question. Can I cancel the x plus 3s here? Absolutely, right? I absolutely can. This just gives me x minus 6, right? Okay, and now my limit theorems kick in. My limit theorems say, hey, the limit of x as x approaches -3 is -3. The limit of a constant is just equal to that constant, and we get -9 for the answer. And that is not equal to f of -3. Okay, so that whole calculation proves, let's just add the conclusion here, f is not continuous at c equals -3 by the huge remark. Certainly just cite that result. By that huge remark, it's not going to be continuous at -3, okay? But let's look at all of the other values of c now. Actually, guys, this function is really just like the one over there with the hole in it. There's a hole at x equals -3. Otherwise, if x does not equal -3, your function is just this equation right here, which is just a line. So it literally is just kind of like that picture that I have over there. We're basically looking at a line that has a hole in it, and the point that is trying to fill that hole is not successful. If this had said -9 right here, we would have been fine, right? Then it would have been continuous at -3. But since I picked a different number, it doesn't work. Okay, so what about, let's assume now that c does not equal -3. Let's assume that c does not equal -3, and let's just do the same thing again. Let's take the limit as x approaches c of f of x. And so this would just be the limit, and this time I don't know what c is, so I'm just going to leave the c in my work. So the limit as x approaches c of the function f of x is essentially x is approaching c, so you could make, you know, a small enough neighborhood around c such that the -3 is not in it. So I can just replace it again with the rational function on top. And that just becomes the limit as x approaches c. It's exactly the same as before. I can factor it again and cancel it again. So I'll write it out. X plus 3 times x minus 6 on top, divided by x plus 3 on the bottom. And that is the limit as x approaches c of x minus 6. Now here you might be wondering, can I really cancel those? Because after all, x is, I know that x does not equal c, but could x equal -3? Because they're not the same value. So you might think, well, x could be equal to -3, but remember that you're eventually going to take, you know, a neighborhood around c that's as small as you want it to be. It can be so small that -3 isn't even in that neighborhood, right? There's a distance between -3 and c. So when you make a neighborhood around c, you can make it very, very small and exclude -3 completely from it. And so that allows you to just cancel. And again, you just plug in c for x right here, and you get c minus 6. That's the limit value, but also if we actually just wanted to calculate f of c, well, we would just use the formula. And since c does not equal -3 in this case, the formula would just give us c squared minus 3c minus 18 all over c plus 3. So it's actually not all that different in terms of the calculation that you're going to do. This is also going to cancel in exactly the same way, it's just gonna give you C minus 6. So these agree this time. These two things agree, so by the huge remark, if they agree, if we got the same thing on both sides, then F is continuous at those points, right? So F is continuous at C. And again, we'll just cite this huge remark. It's getting huger by the minute every time we use it. So far, so good. Okay. Well, I want to do a little bit more with this still, but I think we should probably take a little break first. It's been over an hour already. Why don't we take 10 minutes, let you guys decompress. I'm not going to erase that huge remark though. I'm going to leave it on the board. We're going to keep referring back to it as we get into the stuff we're going to do next. So let's take a break. We'll come back, we'll finish this, and then we'll do some group work.
Would you add the data that when C does not equal?
Yeah, we're kind of in that heading, but if it helps to just make sure we don't lose track of that, certainly add that there. Yeah. Very good. Yeah, maybe what I should do is draw a picture. 3 x plus 6. X minus 6.
To scale.
Not at all. Not at all, but that's kind of the picture of it. Okay, let's take a little break.
You had to learn how to fucking do it.
Yeah.
No, well, I didn't do it. I also didn't do it.
Yeah.
Dude, I was trying to argue with me the whole time. He's like, you can't use the vertex formula, but why not? How can you use areas? Sometimes I can't use the vertex formula. And he's like.
So I did say
Your
negative
prior foundation.
in there.
Yeah.
Yeah, we continuous everywhere, but we still
You
need,
have an equal sign here, and then, yeah. so then the
No.
whole thing would work.
we still need to do both sides.
You probably would do them as two separate cases because this case, you're literally just plugging a number in, you don't have to use the rational function, whereas for this case would look identical. So yeah, it would make more sense to do it as two. When something's piecewise defined, you generally have to do it in two pieces.
You just do another one.
Yeah.
Let's see equal this and
Exactly.
You probably did, you just don't remember everything.
And that's it.
Like, whenever it's formula, you know, well, your data, your original. Yes. Well, very interesting.
Well, guys, I think we might have everybody back. I think I might try and continue here. I do want to make sure I have enough time to let you guys work on some group work today. So, but I do want to finish this section. It'd be really nice to kind of go into the weekend with this kind of finished up. I don't have much more to do, but a couple things I wanted to say. I've kept the huge remark on the board. This is the connection between limits of functions and continuity, right? That's the bridge. And we're gonna milk that and use that as much as possible, right? So let me give you another example. We had a characterization of limits in terms of sequences, right? So you might be wondering, well, is there a theorem about continuity directly related to sequences? Right? Can we characterize when a function is continuous at C in terms of something about sequences that involves C? It turns out that there is exactly such a result. So let me actually state it here. This is theorem 4.1. And so here's what it says. Very simple, right? So let f be a function from a domain D to the real numbers R. Okay, so we're going to make a connection here between continuous functions and sequences. And I'm going to use this. This is the proposition that connected limits of functions to sequences. We're going to need this in just a minute. But I'm going to take my function and I'm going to grab my point C, which is in the domain. Then f is continuous at C if and only if. So I'm going to give you a characterization here. And here's what it's going to say. For all sequences xn converging to C, the sequence f of xn should converge to f of C. All right. Now, I might make a couple of comments here. Again, C could be potentially an isolated point of the domain. That is possible. But remember, if C is an isolated point of the domain, then we already learned in the tiny remark, we learned that at an isolated point, f is always continuous. So this would always be true. And at an isolated point, if you had a sequence converging to an isolated point, then the sequence would actually have to be eventually equal to C, like what we call an eventually constant sequence. And if you have a sequence that is eventually constant at C, then of course the image of the sequence will eventually be constant at f of C. So for isolated points, this is true and this is true, and they are absolutely equivalent. There's really nothing to prove. Why am I saying all that? I'm saying all that because I want to use my huge remark, and my huge remark requires C to be an accumulation point. You can see it in the assumption up here, right? You can see it in the assumption. So let me make that as a quick little comment, and then we'll really get into the actual proof here. So quick remark, if C is not an accumulation point of D, i.e. C is isolated, then F is already continuous at C. There's no mystery about it at all. F is continuous at C by the tiny remark that we wrote down earlier today. So for isolated points, the story is not very interesting. The function will be continuous at all such points. Okay. So that's my first comment. So we can kind of focus more on the accumulation points of the domain. That's more along the lines how you're gonna use this theorem. The other remark I should make, I'm making lots of remarks today. Only one of them was huge and only one of them was tiny. The rest of them are all in between, regular remarks. The other remark is that, again, I made this remark earlier with this proposition. We're not going to be using the backwards direction, right? We're not going to try to prove that F is continuous by showing that for all sequences that converge to C, their images converge to F of C. This would be impossible. There's too many sequences. It would take a lifetime and then some to try to write down every sequence that converges to C and look at what happens to its image. So we will not be proving continuity using this result. If you want to prove that a function is continuous, please try to use this result, or at least use the definition, the epsilon delta definition. Don't try to use this thing here. Rather, the way that you use this theorem is to disprove continuity. So theorem 4.1 is used most often to show, sort of by way of contradiction, I'll say, that F is not continuous at C. So you assume that it is, and then you use the forward arrow, right? So the forward direction is where the power is on this result. To say, well, if your function was continuous, then this very strong condition would have to be true. And all you have to do to disprove that condition is find one sequence that converges to C where the image of this sequence does not converge to F of C. At that point, this fails, so therefore this fails. So you use this in contrapositive formulation or contradiction formulations, usually the way this is going to get used. Okay, kind of makes sense? That's generally how you want to use that. Okay, another, I guess, another remark, I'll call this another remark. I am going to prove this result eventually. I'm not just stalling. It looks like I'm stalling, but no. Really what this says, I just want to give you a catchphrase for what this statement really just says. What it says, guys, is that continuous functions preserve convergent sequences. So if you want just kind of a catchy way to say the theorem, to kind of remember the theorem in kind of a simple way, this result just says that a function will be continuous at C if it preserves convergent sequences at C. So if you start with a convergent sequence and you apply F to it, you still have a convergent sequence. So it's just a kind of a handy way to remember what the theorem says. But I still want you to, of course, have this on a flashcard and kind of be memorizing it. But what you could do is you could, on one side of your flashcard, you could put this. Convergent functions preserve, continuous functions preserve convergent sequences. And then on the back side, state the theorem, right? This is what the result says. Again, we're not going to use this result to prove continuity. We're generally going to use it to disprove continuity. It's generally how it works. All right, well, let's write down the proof of this result, and I hope you guys don't blink or you're going to miss it. It's extremely short. So short, I can fit it right in this little space right here. Forget the double arrow. We're just going to go both directions in one breath, right? So I'm just going to do it all in one breath here, guys. This is going to be so short and sweet. F is continuous at C if and only if. Well, now I'm going to use my huge remark. Now, again, the huge remark only works if C is an accumulation point of the domain. That's why I made my first comment here, which is that if we have an isolated point, then F is already continuous at C, and there's really no reason to work with this theorem. The theorem isn't really very useful. So I'm assuming, let me just say that here in the assumption, guys. Assume that C is an accumulation point of D. Of course, it's also got to be in D itself for F to be continuous in C, but we'll just assume that. So what does this tell us? This tells us that the limit of f of x as x approaches C is equal to f of C. That's what the box theorem, the box huge remark says over there. And I've got this proposition now, right? So by this proposition, 4.6 is this right now. This is the one that tells me when the limit of f of x is equal to some number L. And what's it say? It says for all xn converging to C with xn not equal to C for all n, f of xn converges to, well, whatever the L value is. Well, the L value is f of C. And that's basically the right-hand side. That's basically the right-hand side. For all sequences xn that converge to C, f of xn converges to f of C. We're done. That's the proof. It's just so nice to be able to use the earlier results about limits of functions to now prove all these things about continuity. So that's your proof. Basically, if you wanted to, you could make that all fit on one line. Quite sure. All right. See, we did all the hard work on Tuesday. Today we get to just relax a little bit. We just use the huge remark to sort of be the bridge between these things. Let's show you another example of how this can be so helpful. Let's write down another result here. This is proposition 4.2. Put this one right here. What's this one say? Let f comma g be functions from D to R. So I'll just say be functions. And let's assume that they are continuous at C. That are continuous at some point C in the domain. Assume that they are continuous at C. Then the following are also continuous at C. Number one, f plus g. Number two, f times g. Number three, we're going to take a scalar, I'll call it k times f. So this is just where k is just a fixed real number. Again, we don't really need to do that because you could take case 2 and just assume that g was just a constant function k, but the book lists it out as a separate item. So I'll do that as well. And then finally, number 4 is f over g. And this one is provided, as you would expect, provided that g of c is not 0. We do not want the denominator there to be 0. I don't like this eraser terribly well. Let's try this one. You understand the statement? You add, subtract, multiply, or divide continuous functions, you just get another continuous function. And are you ready for super easy proof? Ready or not, I'm gonna do it. Ready or not, it's gonna go quickly. Well, first of all, I'll address the isolated points thing again. So if C is not an accumulation point of D, so maybe that's possible. If C is not an accumulation point, then remember that everything is continuous. The tiny remark says that if you have an isolated point, then every function that you would define on that domain is isolated. So that would be F, that would be G, that would be F plus G, F times G, all of them, right? They would all be continuous. So that all functions, so if then all functions are continuous at C by the so-called tiny remark. So just using that earlier remark, everything would be continuous. There's nothing left for us to do. Okay, so now we're going to assume that C is an accumulation point of D. Let's assume that C is an accumulation point of D. And if it's an accumulation point of D, then of course we're going to get to use our huge remark over here. So let's just try and do it. So then I want to prove that F plus, so let's start with 1. I want to prove that F plus G is continuous at C. I'm going to do it by using the huge remark. So I'm going to take the limit as x approaches C of F plus G. Well, that's just F of x plus G of x. You know, I'm sorry, I hate to erase because I know it's annoying for you guys. I'm just going to rewrite this as, I just want to make it really explicit. We're looking at F plus G. So I'm going to write it as F plus G of x. Of course, this just means, right? This just means that you're taking the two functions and adding the results. So it's F of x plus G of x. That's just the definition of F plus G. So it's just F of x plus G of x. But what do we know about limits of two functions added together?
Limit of each one.
So limit of each one separately, right? That's the proposition we did on Tuesday, the limit theorems, right? So this one, by proposition 4.7, those are the limit theorems. This is just the limit as x approaches C of F of x plus the limit as x approaches C of G of x. But guys, F is already assumed to be continuous at C, which means that this result is already true for F alone. So the limit of F of x as x approaches C is just F of C. And the limit of G of x, same thing, G is also continuous at C, so the limit of G of x is just G of C. This is the huge remark again. Ooh, we see that a lot today. And that is just F plus G of C. And so F plus G is continuous by the huge remark. You checked the huge remark for the function F plus G now. So that's number 1. That's number 1. Does anybody in here think they could do number 2? Let me ask you another question. Does anybody in here think they could change a plus sign to a multiplication sign and run the whole thing through again? All it is. It's all it is. F times G of x is just F of x times G of x, which is this limit times this limit, which is F of C times G of C, right? It's all just the same thing. I'm just going to say 2, 3, and 4 are similar. If any of you don't feel super comfortable with it, of course, I encourage you to write it out maybe on your own time, but we don't really need to do that here. It is basically the same thing. Turn the plus sign into a multiplication sign. For part 4, you'll turn the plus sign into a dividing by sign, right? And there was in the proposition 4.7, when you divide, there was a proviso that the limit of the denominator has to be not 0. So you've got that here as well. Anyway, so there's no surprises with any of the rest of that proposition. So we don't even have to break a sweat on this. And the reason we don't is because of this result here, which ties what we're talking about today, continuity of functions, back to limits of functions, which we did work hard for the last couple of classes. Right, so that's why we're getting such good mileage today. I love it when, when we can suddenly make this kind of progress here. There is one more result. Do I want to do it now? Do you want to see me, do you want to do some group work or do you want to see one more result today? Results? Okay, so we do, are you okay if we just do the group work on Tuesday? Okay, it won't be too bad. It won't be too bad. I'm excited, so I should just keep going, right? Ride my enthusiasm all the way to the end of class. There's one other thing you can do with functions that I have not been talking about, which is that you can compose them, right? So you can take f of g of x. So instead of adding or subtracting or multiplying or dividing, which is kind of what we've been focusing on here, there's also this idea of composing the functions together. It's not quite as simple to just add it as a number 5 on this list though, because the domains and ranges of the two functions might not even be the same, right? And so we have to be a little careful. So the book actually, I think wisely, decides to state it as a separate proposition. And so I'm going to do that as well. So a separate proposition, we actually are going to need to make sort of 2 domains, one for f and one for g. And the book, I'm going to state it exactly as it is in the book. The book is going to use a and b for the subsets that are going to be the domains of these functions, okay? So let a and b be subsets of R. F is going to be a function from a to R, and g is going to be a function from b to R, okay? Okay, so again, I'm going to try to compose the functions together. If I want to do that, any output of f has to be something that you can then input into g. So I'm going to require that the image of f, if I take f of anything, it has to be ready-made to be plugged into g. So it has to be a subset of b, all right? So now here is the statement. That's just the setup, right? The real statement here is that if f is continuous at c, so if f is continuous at c and g is continuous, anybody have an idea where we're going to want to assume that g is continuous at? At f of c, right? Because the output of f is what we're going to be looking at when we plug into g. So continuous at f of c. So if f is continuous at c and g is continuous at f of c, then when we compose the functions together, this would be g composed with f. I use the little circle for composition. You guys have, I'm sure, seen this before. This is a function from a to r again. And this will be continuous at c. Okay, so just because of the nature of composition, you kind of need a separate proposition for this one, right? We can't just add it to this list because, you know, the domains and ranges and so on are getting all mixed up. So we have this separate statement. In addition to that, I'm actually going to prove this one. I'm not going to use the huge remark for this. I'm actually going to prove this one back to the epsilon delta definition, which, since it's been 10 minutes since I've mentioned it, probably not a bad idea to review it again, right? It's so important. So we're actually going to prove that this is continuous using the epsilon definition, which is actually not on the board at the moment in here, but you've hopefully got it kind of in your notes or in your mind a little bit. Of course, it starts off with let epsilon greater than 0 be given, right? So we'll start off that way. Let epsilon greater than 0 be given. And our job is to come up with a delta. Now, we already know that for both f and for g, we will be able to find a delta because each of f and g individually are already continuous. I'm going to use the fact that g is continuous first. So this is one of these proofs where you kind of work backwards. So you're gonna work on the G first. Actually, it's not really backwards, it's on the outside. Okay, so because G is continuous, so let's just say it this way, since G is continuous at F of C. Since G is continuous at F of C, then there already exists a delta, right? But I'm not going to call this delta, I'm going to call it delta 1, because we're going to actually need to appeal to a couple of different deltas in this group. So I'm gonna say there exists a delta 1 greater than 0, such that if, okay, and I'm applying this to G. So guys, take a look. G goes from B to R. We're looking at F of C as it's like what used to be what we called C. So what this should say is such that if the absolute value, I'm gonna actually use a different letter than X. I'm gonna use a Y here, because those are the outputs of F are inside of the inputs of G. So such that if the absolute value of Y minus F of C is less than delta 1, then because G is continuous at F of C, we would be able to say that the absolute value of G of Y minus G of F of C would be less than epsilon. That's right. Okay, so if Y is close to F of C, then G of Y is close to G of F of C. That's what continuity means from a definition point of view. Okay, so that's the first part. Okay, so we're getting there, Now, since F is continuous at C, that was assumed as well. Since F is continuous at C, there also exists a delta. Now, this time I am actually going to call it delta. You might think I'm going to use a delta 2 here. And a lot of times we will do that, and then we'll take a minimum of those deltas. We don't need to do that here. This is actually going to be our final delta. This is going to be the final delta that we need. There exists a delta greater than 0 such that if the absolute value of X minus C is less than delta, then the absolute value of F of X minus F of C is less than whatever I want to put here. Right, I can put whatever I want to put right here. I don't have to put epsilon. I can put something else that I have, and I'm actually going to put delta 1. I can use that, right? Delta 1 is just as good as of a positive number as epsilon was. So that's a little trick. That's a little trick right there. Okay. But now that I've got that delta, I'm going to try to show that the composition of G with F is continuous at C by proving that that delta works. So let's do that. Let's assume now that absolute value of X minus C is less than delta. And then what I need to look at, what I have to calculate, guys, is I have to calculate, well, what is the absolute value of G composed with F of X minus G composed with F of C? This is what I gotta look at. This is what I have to show. And I want this to be less than epsilon. I want it to be less than epsilon. That's what I need to prove. I started with epsilon. I've got to ultimately show that G composed with F of X minus G composed with F of C is less than epsilon. This is how the definition works. It's too bad. I should have had the definition on the board. But anyway, that is just the definition of continuity at C. Let's just write down what this is. This is the absolute value of G of F of X minus G of F of C. Certainly just write that down. And do we know anything about that? As long as the distance from y to f of c is less than delta one, I can say something here. Is there anything that's within delta one of f of c? F of x is. How far away is f of x from f of c? It's less than delta one. So this statement right here that I'm underlining actually applies to the case when the y value is just f of c. If y is the same as f of c, I already know that f of x minus f of c is less than delta one. So if I plug that here, f of x minus f of c is less than delta one. So that means if I put f of x here, this statement is true. Which is actually exactly what we have right here. This is already less than epsilon. Let me just add a little bit here. This is since we can put f of x into the role of y above. And that is since the absolute value of f of x minus f of c is less than delta one. So it's a little tricky. It's not quite as standard as some of the other results. Okay, but that's how that works. Questions on that? Well, we only have a couple minutes left. I think I'm just gonna do one last example to kind of send you off into the weekend. We've done a lot of material this week, guys. Be sure to study your notes. Between now and Tuesday, you don't want to just spend 4 days off in no man's land and then come back on Tuesday. You'll feel much better if you've spent a little time on this material over the weekend. That's for sure. But let me just finish with an example. I always like to come back to something nice and concrete here. I'm going to consider a function h, which goes from R to R, defined by, so this will be our last example for the day, h of x equals, it's piecewise defined again. I'm going to use x times the sine of 1 over x. This will be if x is not 0. And if x is 0, we'll just make h of 0 equal to 0. And the claim is that h is continuous at all real numbers, all c values, all c in the real numbers. That's the claim. That's the example I want to just kind of wrap up with. And this is not long at all. Okay. By the way, this, just so people have a visual of this in their minds, what this graph would look like if I was going to plot it on an XY coordinate system. The sine of 1 over n, of course, the graph of sine just kind of oscillates from +1 to -1 in this nice wavy motion. But because you're taking not sine of x, you're taking sine of 1 over x, very small changes in x that are close to 0 create very large changes in what you're taking the sine of. And so what happens is the ripples get really, really tight. And so your graph, if it was just sine of 1 over x and I just wanted to graph sine of 1 over x, the graph would look basically like this. But then when you multiply it by x in front, that x has the effect of kind of damping it down when x is small and stretching it up when x is big. So what this graph actually looks like is something kind of like, not a good start. Let's try that again. The graph actually looks kind of like this. And the waves get much broader as you get far, far, far out to the sides. So it's very, very tight wiggles. And they're not very tall when you're close to zero because of this X that's in front here. That kind of multiplies the sine function down and makes it very, very close to zero. But I can actually draw this entire graph without picking up my pencil. That's the idea here, is that this actually is a continuous function for every real number. And so let me just write a couple of quick words about this. Let's get kind of a proof here. Well, if C does not equal zero, if C does not equal zero, then my function is really what? It's X times the sine of 1 over X. What is that? That involves a multiplication, a reciprocal, which is really division. The sine is a continuous function as well. I know I didn't really prove that yet. But sine is continuous, 1 over X is continuous. This is a composition. Proposition 4.3. This is a composition of two continuous functions. 1 over X is continuous as long as X doesn't equal zero. Sine is continuous. You compose two continuous functions together, it's continuous. And then you multiply it by X, which is also continuous. And the product of two continuous functions is still continuous. So what we can say is H is continuous at C by propositions 4.2 and 4.3. And I'm going to make a note here that sine of X is continuous on R. And I am going to show you that next time. What is the next date for meeting? The 18th? I'll prove that next week. We have to use a little trig identity to show that. I'll do that next time. It's not something I need to do right now. But that's it. So you just have your H of X is just a composition and a product of continuous functions. So it's continuous. What about if what if C does equal zero? That's the only other point you have to worry about. I want to prove that H is continuous at zero. I'll do that from the definition. Let epsilon greater than zero be given. I then have to come up with a delta. And I'm just going to, since I'm running out of time, I'm just going to tell you what the delta will be. We actually could just choose delta to be the same as epsilon. And then let's just check that that works. If the absolute value of X minus C, but C is zero, so it's just that. There is no subtracting C here. If that is less than delta, then what can we say about the absolute value of H of X minus H of C? By the way, H of C is, well, let's just subtract it here. H of X minus H of C. H of C is just zero. That is given from the function. H of zero is just zero. Sorry, this should say H of zero here. I'm going a little fast, sorry. H of X minus H of zero. But H of zero is just zero. So this is just absolute of H of X. If you take the absolute value of what you've got right up here, the sign is between -1 and +1. So would you agree that this is less than or equal to the absolute value of X? This is X times something that makes it smaller. So this thing is less than X itself when you put absolute value bars around it. And that's already less than delta by assumption. And delta is equal to epsilon. So you prove just from the definition that H is continuous at zero. H is continuous at zero. So that's a nice example. I was mostly trying to show you the first part, that those two propositions allow us to take weird combinations of things that are continuous. You can add, subtract, multiply, divide, and compose continuous functions, and you still get continuous functions. Is this starting to feel a little more like calculus, guys? We're getting there. Wait till next week. Next week, we're going to do the extreme value theorem. the mean value theorem, the intermediate value theorem, a bunch of other, the boundedness of continuous functions. We have a lot of big results to prove next week, which are really, really nice. You're gonna see hardly a single delta or epsilon next week. Next week, it'll all be much more broad view. I think you'll really enjoy it. Take a break from this technical stuff. That's it for today, guys. Sorry to run you a little over, but I just wanted to get that in. I appreciate it. Have a great rest of your day. And if you get started on the homework a little early and you want to ask me any questions,